Today, we're going to crack a cosmic code. We're going to figure out how the color of a distant star, that tiny little speck of light, is actually a secret thermometer telling us its temperature from billions of miles away. And the key to it all is this amazing piece of physics called Wien's displacement law.
I mean, really think about that for a second. When you look up at the night sky, how on earth can an astronomer possibly know how hot a star is? We can't just send a probe or stick a thermometer out there across light years of empty space, right? So what's the secret? Well, that's the exact puzzle we're going to solve together.
So here's our game plan. First, we'll dive into the biggest clue we have, something called black body radiation. Then we'll bring in the law that explains everything, Wien's law. We'll take a quick peek at the super simple formula behind it, and then, finally, we'll use it to solve our big mystery and take the sun's temperature.
Okay, so our investigation starts right here, with our first and most important clue, black body radiation. Now, that sounds pretty technical, I know, but it's really just a fancy term for a simple truth you've seen your whole life. When things get hot, they glow.
Now, to understand this glow perfectly, physicists came up with this idealized object called a black body. In theory, it absorbs every bit of energy that hits it. But here's the cool part. When it heats up, it also becomes a perfect emitter of light. And this is the absolute key. The color of light it gives off depends only on its temperature, not what it's made of, just how hot it is.
And you've totally seen this in action. Just think about an electric stovetop. At first, it's black, right? But it's already giving off invisible infrared light. That's the heat you can feel. Then you crank it up, and it starts to glow a dull red. Get it even hotter, and it turns that bright, fiery orange-yellow. And if you could somehow get it way, way hotter, it would blaze with a brilliant white-blue light. See? The color is literally a thermometer.
So we have this connection between heat and color, but how do we turn that observation into an actual scientific law we can use? Well, that's where the German physicist Wilhelm Wien comes into the picture. Back in the 1890s, he's the one who figured out the precise mathematical link between an object's temperature and the exact color of light it shines with most brightly.
And the core idea is beautifully simple. Before we even look at the math, this is the main thing to remember. Hotter objects give off light with shorter, bluer wavelengths. Think of a rainbow. Red has a long wavelength, and blue and violet have short ones. So as something heats up, its peak color literally shifts from the red end of the spectrum over toward the blue end. Okay, it's time to peek behind the curtain and see the actual math that turns this idea into a powerful tool. This is the simple equation that lets us calculate temperature just by looking at light.
And there it is. Looks pretty simple, right? That's because it is. That Greek letter, lambda max, just stands for the peak wavelength, which is basically the most intense color the object is emitting. T is its temperature in Kelvin, which is the absolute temperature scale scientists use. And that little b, well, that's the secret sauce that ties it all together.
This b is called Wien's constant. It's kind of like the magic number, the universal translator that makes the whole equation work perfectly. It's this fundamental constant of nature that connects the wavelength of light to the temperature of whatever is spitting it out.
All right, we have the clue, we have the law, and we have the formula. It's finally time to go back to our original mystery and use this incredible tool to measure the temperature of a star. And what better place to start than with the one we know best, our own sun. So let's actually do it. Let's put this amazing law to the test. Can we really figure out the surface temperature of the sun using nothing but the color of its light? Let's find out.
It's really just a simple three-step process. First, astronomers use a special instrument, kind of like a super high-tech prism, to find the sun's peak color. And get this, here's an amazing fact. The sun's peak wavelength is around 500 nanometers, which is actually green light. The reason we see it as white or yellow is because our brain just mashes all the colors of its spectrum together. So, step 2, we just rearrange Wien's little formula to solve for temperature, and step 3, we just plug in the numbers.
And what you get is about 5,800 Kelvin. That's over 5,500 degrees Celsius, or almost 10,000 degrees Fahrenheit. Just let that sink in for a minute. We just calculated the temperature of a giant ball of nuclear fusion 93 million miles away just by looking at its color. That is the incredible power of Wien's law.
So let's just recap the mission here. We figured out that an object's color is basically its thermal fingerprint. We learned that Wien's law is the secret decoder ring that lets us read that fingerprint, and we saw how this one elegant idea became a cornerstone of modern astrophysics, letting us unlock the secrets of the most distant things in the universe.
And that leaves us with one last really fascinating thought. If just looking at a star's color can tell us its temperature, what other secrets are coded into that ancient starlight? What's it telling us about what it's made of, how it's moving, or how old it is? That light is a cosmic message, and it's just waiting for us to read it.